To finish with this module, we're going to just look at a little bit of algebra involving exponential and logarithms. Namely, we want to solve equations and inequalities. I'm not going to do any theory about that, but just go over some examples to illustrate how you would proceed if you have to solve equations or inequalities involving these functions. So to start with, we look at a series of equations that involve either an exponential or a log, and we want to solve. In other words, find all the x's for which the equality is satisfied. And we start with the equation e to the 2x plus 3 minus 7 equals 0. So in general, when we have just one exponential or one natural log, we're going to try to isolate it to start with. So in that case, we get e to the 2x plus 3 equals 7. And then, of course, this can be rephrased in terms of logarithm, because we can take the natural log on both sides, and we get the equivalent formulation that the natural log of e to the 2x plus 3, which is going to be just 2x plus 3, is ln of 7. This should be an if and only if, because the natural log is 1 to 1. Therefore, if we have equality for the logs, we have equality for what's under the logs. So that means 2x plus 3 is equal to ln of 7. And now we've converted our exponential equation into a linear equation. So here we just subtract 3 divided by 2, and we find as a unique solution x is 1/2 of ln of 7 minus 3. In the second case, we have a natural log equal to a constant. So here we don't have to isolate it, it's already isolated. One thing I want to mention is that I didn't care about the acceptable values for x in the first case because x's were only present in the exponential function, and the exponential function is defined on the entire real line. But in the case of logs, you have to be a little bit careful about the domain of your equation. In other words, what kind of x's can be plugged inside your equation. In that case, we plug 5 minus 2x inside the log. That means that this expression, 5 minus 2x, has to be positive. In other words, x should be less than 5/2. So with this in mind, we have our natural log already isolated, so we can just take the exponential on both sides and we get the equivalent reformulation that e to the ln of 5 minus 2x, which is going to be just 5 minus 2x, is equal to e to the negative 3. Once again, that converts my logarithmic equation into a linear one. So I have 5 minus 2x is e to the negative 3. I'm going to add 2x on both sides, subtract e to the negative 3 on both sides, divide by 2, and we obtain as a unique solution x equal 1/2 of 5 minus e to the negative 3. Now you see that this is indeed a value that is less than 5/2. This is something that we should verify that the solution we obtain is indeed in the domain for the equation. Of course, this is 5/2 minus 1/2 of e to the negative 3, and exponential of whatever number we pick is always positive, so it's 5/2 minus something positive is less than 5/2. Now for the third equation, we have e to the x equal 10. Again, we have an exponential that is isolated, equal to some constant. And I don't have any problem of domain because it's just exponential. So I take the log on both sides, I get an equivalent reformulation that ln of e to the x is ln of 10, and my ln of e to the x is just e to the x, so I obtain that e to the x is ln of 10. Well, I'm going to do the same thing again, take the log on both sides, and I get that log of e to the x, which is going to be just x, is ln of 10. In other words, x equal natural log of 10 is the only solution to this equation. In the fourth case, we have something of a slightly different nature because we have two different logs, and therefore we cannot just isolate one log and then take the exponential on both sides because we have two of them. First thing we have to do when we have equations involving logs is make sure that we know what the domain for the equation is. So in that case, the domain is the set of x's that we can plug in. So in order to be able to plug in 2x plus 1 into a log, I need x to be greater than negative 1/2. And on the other hand, in order to be able to plug x into a log, I need x to be positive. So I need both conditions that x is greater than -1/2 and greater than 0. Of course, if it is greater than 0, it's also greater than -1/2, so the condition is really just that x is a positive number. So that's the domain for our equation. Now here is our equation, and as I said, we don't have just one single log. So we need to somehow try to combine them to get to the situation we had, for instance, in the exercise number 2. But it's not hard because I can put the two logs on the same side and I get ln of 2x plus 1 plus ln of x. And then we can remember that among the logarithm laws, one of them states that if you have natural log of a product is the sum of the logs. So looking at that the other way around, I have a sum of log, it's the log of the product. So the log of the product, x times 2x plus 1, is equal to 2. And here we should keep in mind the condition that x is positive, because x times 2x plus 1 is going to be also positive, in other words defined to plug in inside the log. If, for instance, x is negative and 2x plus 1 is negative, then the product is positive. Right, so we have to keep in mind the domain here when we do this kind of manipulation. Okay, so now I have a single log equal to a constant. I do the usual thing, take the exponential on both sides. And on the left hand side, I just have e to the ln of something, so I just get this something which is 2x squared plus x. On the other side I have e squared, so I get 2x squared plus x minus e squared is 0. So that's a quadratic equation, and we know how to solve quadratic equations. We can use, for instance, a quadratic formula. To do that, I'm first going to calculate the discriminant, which is this b squared minus 4ac, this quantity that you plug inside the square root in the quadratic formula. So here b squared is 1 squared, and then I have minus 4 times 2 times -1, so I get plus times -8e squared. So I get 1 plus 8e squared, and that's certainly positive. So I'm going to get two real solutions that are -b and it's -1 plus or minus the square root of the discriminant divided by 2a, which is in this case 4. So it looks like we have two solutions, but again we have to be careful. The domain of the equation is x positive, and you see that among these two solutions one of them is negative. If I take -1 minus a root, this is going to be negative. On the other hand, the root of 1 plus 8e squared is certainly greater than root of 1, which is 1. So that means that -1 plus root of 1 plus 8e squared is positive. So we have just one positive solution, which is this, -1 plus the root of 1 plus 8e squared, or this over 4. And that's a unique solution for this equation. For the fifth equation to solve, again we have two different exponentials, so we're not in a case comparable to 1 or 3 where we could just isolate a single exponential and take the log on both sides. We don't have an issue for the domain because we only have exponentials and they're defined everywhere. But we need to find a way to combine these exponentials in some way. So first I'm going to rewrite the equation this way, put everything on the right hand side, and I get e to the 2x minus 7e to the x plus 12 equals 0. So you may or may not recognize an equation that is quadratic in form, but it is, because e to the 2x is nothing but e to the x that you square. Now under this form we can let u be e to the x and we obtain a quadratic equation of the variable e to the x equal u. This equation here is u squared minus 7u plus 12, which is easy to factor as u minus 3, u minus 4. And so the equation becomes u minus 3, u minus 4 equals 0. In other words, u equals 3 or u equals 4. We go back to what it means for x. It means e to the x is 3 or e to the x is 4. And we can write that in logarithmic form. Take the log on both sides and we get x equal ln of 3 or x equal ln of 4. And these are the two solutions to our equation. To conclude, I just want to say just a few words, I'm not going to dwell on that very long, about inequalities that involve natural log or natural exponential. So let's say we want to solve 2 is less than ln of x is less than 9. So here solving means find all the x's that satisfy this inequality. The key thing to remember to solve this kind of inequalities is that e to the x and ln of x are increasing functions. Now what does that mean to be an increasing function? It means if x1 is less than x2, then f of x1 is going to be less than f of x2, right? Because when you move from left to right for the x values, you move up for the y values. In other words, you preserve the direction of the inequalities. So that's really all we need to remember. E to the x and ln of x are increasing, they preserve inequalities. For instance, for the first one, I have 2 less than ln of x less than 9. I can apply the exponential to each term in this sequence of inequalities, and because the exponential function is increasing, it's going to preserve the inequality. So I get e squared is less than e to the ln of x is less than e to the 9th, which means that x is between e squared and e to the 9th. Or in other words, the solution set is the interval, the open interval from e squared to e to the 9th. Similarly, for the second one, we have an inequality with an exponential. We're going to use the fact that the natural logarithm is increasing and therefore preserves inequality. Namely, I apply the natural log on both sides of the inequality. It preserves the direction of the inequality. And on the left-hand side, I have natural log of an exponential. That's the identity. So I get 2 minus 3x greater than ln of 4. And now this is simply a linear inequality. So I can, for instance, add 3x on both sides, subtract ln of 4 on both sides, divide by 3 on both sides, and I get that x is less than 2 minus ln of 4 divided by 3. In interval notation, that means the solution set is the interval from negative infinity to the number 2 minus ln of 4 over 3. And that doesn't include this endpoint. Now we're done with this first module, and it's time for you to turn to homework.